To get more into the carbon cycle, we've used this terminology biogeochemical cycles before, because there is biology involved, there is geology involved. We will see how the elements are recycled, and there is chemistry involved. And the key thing here is recycling of elements. Okay, so biology takes up some elements, it dies or is being eaten, or it produces fecal pellets, like we produce feces, which have nutrients, carbon, nitrogen, phosphorus, etc. And those are recycled, remineralized back into inorganic nutrients and carbon and being reused in the system. You get many schematics of global carbon cycle. This is a simple one which is just showing the processes. So we have volcanic activities, which are very episodic injection of carbon dioxide along with sulfur dioxide, methane, ash, and dust and so on into the atmosphere. We called it the external forcing because elements from buried within the earth are being thrown into the atmosphere and they change the radiation budget. Remember, forcing means it has to change the radiation budget, right? So there is respiration and photosynthesis on land and in the ocean. And the ocean is much more three-dimensional, so you have organic matter falling down, being consumed, recycled, and as we will see a little bit later on, a tiny, tiny, tiny fraction of it makes to the bottom. And even after it makes it to the bottom, there are microbes which respire the hydrocarbons or photosynthesized carbohydrates, and some of it gets buried because more sediments or more organic matter falls on top. On land, obviously, we are having river transports, but here it's not just the organic matter, it's also the weathered products of carbonate, bicarbonate, calcium ions, and so on, because we're talking about the carbon cycle here, not just nutrients and biological matter. So there is weathering and erosion relating to that. Plays a key role on a longer time scale. For everything, we have to look for what would prevent moving things in one direction. What are the feedbacks that maintain equilibrium, and at what time scales they work on? So ocean has precipitation of skeletons, dropping of organic matter, and so on. You get many schematics like this which have numbers. So here it is showing atmospheric increase in terms of petagrams of carbon per year. Peta is 10 to the 15. You can say gigatons or petagrams. You can use different units. So we're not talking about concentration in ppm here. We are talking about the reservoir size in petagrams carbon. Okay, and we are showing fluxes. So we are looking at reservoirs and the fluxes between them. So you have ocean floor surface sediments with 1750 petagrams with a flux of 0.2 petagrams per meter squared per year from the surface ocean into the intermediate and deep seas. So you can see the intermediate and deep seas have a massive reservoir of 37,100 petagrams. Surface ocean is much smaller, and there is a flux of downward flux of 90 petagrams, upward flux of 101 petagrams, and the atmosphere and ocean are exchanging about 80 and 74. So photosynthesis, exchanges, etc. is taking up about 80, and the ocean is belching out globally average about 17.7. Well, sorry, total of 78.4. Why does it matter? Because the net flux, ocean flux, is only 0.7. So going in is 2.3 plus minus 0.7, and going out is 0.7. So when you want to estimate the ocean's ability to take up carbon dioxide, you're looking at a small difference between two large numbers, what is going in and what is coming out. This is what makes it very difficult because you have a huge ocean and there is exchanges everywhere, as we will see again and we have seen before. There are places like the Eastern Pacific where CO2 is coming out of the ocean because there is upwelling, increased partial pressure of surface CO2, surface PCO2, and the difference in the atmosphere and ocean PCO2 or partial pressure of CO2 determines the direction of the flux. So when you have two large numbers and you have to track the difference, you need lots of measurements. So there are all these various boxes: burial on land, river flux, biological flux versus solubility flux, dissolved organic carbon being moved around, and here is the fossil fuel reserves that we are burning up in terms of gas, oil, and coal, and we are burning at about 365 petagrams carbon per year. So atmospheric increase is about 4 petagrams carbon per year, and just to give you a sense, I'm not going into all the details, but here are emissions from human beings, deforestation and burning, weathering. So there are sources and there are sinks. Volcanoes have a tiny bit of a source, but they have played a critical role in the past in terms of what they did during ice ages and so on and so forth. So even in land, you can see that there is a downward flux of 2.6 with a high uncertainty of plus minus 1.2, and there is the so we're talking about anthropogenic flux and natural fluxes, and again you are talking about difference between two large numbers. This is what we have to worry about. Measurements, 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 lots of data needed to know for sure what the uncertainties are in the fluxes, because we need to track very closely the sources and sinks, because we know how much CO2 we emit, but we need to track where it is going and how much remains in the atmosphere.